All right, welcome back. Did you guys have a good break? Yes, no, needed. All right. I had a great time as well. It was, for me, it was a combination of work, service, and vacation. So it was fantastic. Didn't shave all week, so I figured I'd do this. Haven't done this in a while. Already irritated with it, so I'll probably come off in a day or two. But I did not get to any grading. So I was doing other work and some vacation. So didn't do any grading, but I'll be working on that this week. So hopefully you'll get exams and your homework grades back to you probably sometime next week. Is likely. So if we take a look at where we are with the semester, heard somebody saying it's not so much time left. Certainly appears to be true when we take a look at our syllabus here. Today we're going to talk about metals in water. What are these so-called complexation agents? What's a chelating agent? What's a ligand? What kind of chemistry is going on here? Why does it matter? All that. So we're going to today talk mostly about kind of the concepts. What is this? Why does it matter? What happens? Next time we'll probably get into a little bit more of the solubility. Okay, let's calculate something. Let's draw a graph at what range of pHs or other schemes are our metals going to be soluble, that type of thing. Okay, so today mostly it's kind of the concepts. All right. Next time I think we'll probably do something we could analyze graphically or make a calculation about. From there we'll go on to redox chemistry. That ties pretty closely with metals. A lot of redox reactions involve metals, as we'll learn. And then we'll conclude with a carbonate in water, which kind of ties back to a lot of what we've done in the past and gives us a good, pretty direct example of a diprotic acid system. So we're going to try to piece all these together. Carbonates also have a lot of impact on solubility of other minerals and redox reactions as well. So I think that'll tie it up together pretty well. So that's the plan. One of these redox lectures might get converted to let's talk about exam 2, or at least partly. So that might also happen. Okay, how do you guys feel? Ready to be done? Okay, so we'll get there, promise. Okay, so that's what I have to say for that. I think I'll probably revisit with you at some point in here how we're feeling about MATLAB and give you a more formal assignment to do something in MATLAB. Okay, now that I think by now you've gone through all the trainings, or maybe there's like one last one or something like that. So hopefully you're feeling good about that. Maybe we'll do kind of like we did with Excel, work it out together to an extent to see, okay, this is how I might build some MATLAB code to do a thing. Done a little bit of that in the past, but want to get you guys a little more applied to say, okay, I'm going to build that and make it graph what I want it to. Happy about that? Feel scared? Anybody? Feel excited? Not excited? Don't care at all? Let's get this over with. A lot of people want to raise their hands, but they're too polite. Oh, there we go. All right, got one. Or maybe it was hello, I don't know. Okay. All right, so we'll get going with what are we talking about with the metals. There's quite a few topics here that we could consider. This is chapter 9 of our book. Basically, most of these we'll touch on. There's a couple that I'm not really planning to go too deep on. These ones I'm kind of shading out a little bit. So we'll talk about what does this coordination number mean. Talk about the fact that we are getting some central metal ion and then molecules are coordinating around it and stabilizing it. We can classify those as monodentate, bidentate, and multidentate ligands. Talk about chelates or chelating agents, which are just ligands of a particular type, and kind of how to describe the strength or the the equilibrium constants for these chelating agents. Okay, so each time we have some molecule that chelates onto a metal, there's going to be some strength there to that interaction. There will be some equilibrium chemistry there. And is it easy to come back off? Is it really sticking strongly? That's going to tell us how well it stabilizes that metal from precipitating. So it'll keep it in water better. And we'll talk a little bit about physically what it looks like. What is this inner shell versus outer shell, or outer sphere, inner spheres complex? It's basically whether or not water is the first layer. Okay? So a few concepts here, and we'll take a look at some ugly looking derivations for this stuff, but really you've done this kind of stuff already. So if we just don't worry about trying to do it all ourselves at the moment, we can follow along with what the book shows us and say, oh, okay, I kind of see what's going on. I wouldn't want to do all that derivation myself, but you've kind of done these types of steps. So we'll take a couple slides to look at that too. Okay, so a ligand is the fancy term for some chemical that grabs water, grabs a metal. Okay, this could be water, this could be chloride, this could be all sorts of things. So when that ligand connects to a metal, it's not a covalent bond where it's stuck kind of forever. It's a relatively loose one that it could shake back off. Okay, so it's going to be something like hydrogen bonding or things like that, where it's going to go ahead and share a pair of electrons because it's a favorable thing to do, but it's not too hard to pull it back off, typically. So we are going to call a molecule that has a favorable interaction with a metal ion, we're going to call it a ligand, L-I-G-A-N-D. And when you get ligands on a metal, we're going to call that complexation. We formed a metal ligand complex. The simplest one would just be water. You can form a complex of metals with water. In fact, really, metal ions don't actually stay in water just free floating. There's always going to be something kind of attaching, whether that's a water molecule and maybe the water molecule loses the hydrogen so it becomes an OH minus, a hydroxyl. Something's going to happen. So this is going to be an equilibrium reaction, and we'll see that we could have competing equilibrium reactions if we have something else other than water that also might like to stick to the metal. Well, then we have two equilibrium reactions, one with the water and one with the other thing, competing about who's going to attach to the metal. So metal ions tend to be or act like Lewis acids, meaning they can accept an electron pair. So metals are typically going to have some positive charge, and so they're going to be happy to say, okay, let me share some electrons with you. You have some negativity, I have some positivity, let's get together and share this, and we'll all be a little more stable. Now, the ligands then are somewhat electronegative typically, and so they'll kind of act in reverse as a Lewis base, where they are donating their electron pair. And it's a little bit more of sharing than completely donating, right? So we have a central metal ion, and for example, in this little diagram, we have the M for metal right in the middle. And everything around it here this looks like one big molecule, so one ligand molecule, and as we'll see, this would be a chelating agent. Chelating kind of means claw, like we'll talk about. So it's just grabbing that metal ion and stabilizing it. So it doesn't have to interact with water directly. So that's the central metal ion would be the metal that we're talking about. And it's going to inherently have a positive charge if not interacting with anything else. And then we'll have one or more other ligands, something that's going to donate electrons instead of accept them. Now we can describe each metal as having a coordination number. That's a fancy word to say how many sites will it interact with this ligand type of situation. So can it coordinate with 2 other molecules or 6 other molecules. That's the coordination number. That has to do with the electronic structure of the metal atom. So you can imagine some heavy metals have very, if you remember from chemistry, like SPDEF, all those electron orbital stuff. It just has something to do with that. So you can get some funny ones, like uranium, I think can do like maybe 12 or something. But typically it's between, I think, 2 and 6. Okay? So you're going to have a few sites where metals are happy to share an electron pair. So we can call that coordination number Cn, and that's what it's referring to. So if we look at this little metal in the example, we can kind of look at each bond, right? So we highlight a bond here, 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 and here. So that's 6 sites where we are binding. So that would be the coordination number would be 6 for that metal. Okay. So the complexation affects the solubility of our metals, and that's really why it is important. So some metals will not like to be in water normally. You can even think of gold. It's highly insoluble. It's not almost ever going to dissolve. But we can actually have a tiny bit in seawater given that it can complex with chloride. And we'll see an example of that in a minute. So in order to stabilize a metal, or if we want to destabilize a metal, we have to know what's going on with the complexation. So water itself will do it if nothing else will. You can get waters here. Again, we have a coordination number of 6 on this example. Typically, it's 4 to 8 is the most frequent. Like I said, you can go down to 2 or up to 12 or something like that. And we will typically classify our ligands based on how many bonding sites they have. So water is very simple, has one bonding site that it can share with a metal. So it's a monodentate. Mono meaning one. Dentate, you can think of like dental as kind of tooth or something. It's one site. It's one spot to work with. So bidentate would be 2 spots, 2 bonding sites, or multidentate. So if we're going with the dental analogy here, you could think of these like, chelating means a claw, so maybe if we're using the dental, maybe it's not a claw, but like a toothy mouth. Chomping down on that metal. Okay. So chelating, this is from claw, I think it was Latin or Greek, something like that. Effectively means claw, so you can think of a little claw in your little arcade or something where you're trying to grab the stuffed animals and they never do it because they're programmed to not actually use any strength until once in a million times. Then they actually grab, that's a pretty good example of chelating agents because some of them are going to grab tight and have a very good bonding and firm grip, and some could be loose, right? Yeah.
So the complex is the metal as a central ion with the ligand or the ligands around it.
Yes.
And the coordination number is the bonding sites on the metal itself, but the ligands can also have bonding sites like independent of the metal.
Yeah, great question. So let me clarify here. So a metal can have some coordination number. That's how many spots will be filled by ligands or will be attached to ligands. And so in this example here, in A, zinc has a coordination number of 4. So it's going to want to have 4 bonding sites where it's complexed with something. Okay? Now, you can fill that with different somethings. You could have water, you could have, in this case, ammonia, or you could have something crazy big molecule like this, right? This particular one looks like it has, this would be a multidentate, meaning there's 4 spots that are bonding with this iron here. Now, if that does it to zinc, okay, zinc wanted 4, we're good. But you could have a different situation where maybe the metal wants 2 more, and so 2 waters might fill the place. But when we're describing the ligand, we would say that's a multidentate. It can bind in more than one spot. And if we're describing the metal itself, it's a coordination number. Maybe a better example is B here. So we have zinc again in this example, and we have zinc. It's sharing 4 bonds, or 4 sites where it's bonding. And if you notice, 2 of those are just water. OH2 and H2O, right? Then these other 2 are bonded with a larger molecule. So in this case, we have a bidentate ligand. Yep. And 2 monodentate ligands, just water, complexing it. Yeah. Good clarification there. So it doesn't all have to be the same one. You can see a few other examples here with zinc. We have two of the same bidentate there. And then this last one is one large molecule that's binding all 4 sites. Okay. Now, when it comes to defining how strong these are, there's a few rules of thumb. We would typically say if you can make a nice claw grabbing multiple spots, up to an extent, the more spots you have that are binding, the stronger the grip. If you go really far, eventually the molecule has to contort in weird ways to wrap all the way around the molecule, and then you're probably losing strength because it's just not a favorable arrangement. So if you were trying to, if you've ever tried to palm a basketball, right? If your fingers are long enough, your hands are big enough, you can grab it, and you can imagine the longer they are, the more spots you can grip, the easier that is. So if you grab a tennis ball, you can say, oh, okay, I grabbed that. Now, if you then took something that wasn't a hand, it just had some sticky pads, but it was like, I don't know, something that's kind of rigid, and you were having to bend it to stick, and you try to wrap it all the way around your tennis ball, it's not going to work so well because it's going to want to go back to flat, right? So even though it has a lot of sticky places, that's just not going to work very well. So that's why having a multidentate ligand you're trying to get 10 spots to attach, it's probably not going to be a very strong bond if it does bond. So there's and we would call that steric hindrances. So there's some reasons why if you have a few spots, it's favorable. If you have 1 or 2 spots, it tends to be weaker than something with like 5 or 6 spots. Okay, I think I have more slides to kind of give us a good categorization like that. Okay. So why is it important? Well, there's some chemical, there's some ecological, there's some process reasons why it can be important, even dietary reasons. So when we complex a metal, it can affect the net charge. So if we have a ligand that has a charge, something like chloride, that will affect the net charge of the metal. So that could then affect what else it interacts with. Gold in seawater is a good example. So we can have gold bonding with chloride, either with 2 or with 4, given that gold tends to be in oxidation states of +1 or +3 if it's going to be in water, which it really does not like to be. So that means you could have AuCl2-, that's got a 1- charge because the gold itself is +1, and you have 2 negative charges, right? So you get a net -1, and that would be kind of a linear shape. It would look something like Cl sharing a bond with gold and another Cl. So it might look something like that, yeah.
Would the negative charge try to make it attract an electron donor? Or an electron acceptor?
Generally, in general, that's true. And if you have an electronegative something, it's trying to grab electrons, right? Or is that what you said, or do you say that differently?
Yeah, it's trying to like say like sodium or something. It's trying to like, but can it not have three bonds? Or
It's not necessarily going to bond with the sodium. It might draw it closer. You know, might have some favorable proximity type reactions or interactions, but it doesn't mean it's bonding with it. Okay, so in this example, gold really doesn't love to be in this state. It's really actually just happy kind of being a solid. But if you do get it there, like in the oceans, you could actually consider, well, I wonder if we could extract gold from the ocean. And some people have looked into this. Theoretically, it's possible. I don't think it's economical because if you take a look, we only have about 0.4 nanograms per liter. That comes out to be 10 to the minus 11.7 moles per liter. So if you wanted 1 gram of gold, essentially you'll get half a gram if you collect all of the gold out of 1 billion liters. Okay? So take 1 billion liters, you'll get 0.4 grams, typically. And that's if you get a perfect 100% of the gold extracted. So add in some losses, you know, you're looking at a pretty expensive operation, very likely. And then you have to calculate, well, how much does it cost to treat a liter? And can I do that 1 billion times? And then compare that to the price of a gram of gold. And we often think of gold in the like ounces, and we're thinking, oh, $2,000 an ounce or something like that. But anyone remember what the ounce to gram ratio is?
There's what, 28 grams in an ounce?
That sounds right. It's probably 28 times smaller than that, right? So 1 gram, maybe that's, I don't know, $100 of gold. So 1 billion liters. If we have a good way to extract it, maybe. I don't know. So you can see it's potentially environmentally relevant. This is why we have some gold in the seawater. So lots of chloride, favorable, you know, can get some of it, but not perhaps a relevant economic system there. Okay, so in that regard, you can increase the total the metal in solution, the total concentration of a metal in solution by adding some ligand. And that's one thing to be potentially interested in if we are trying to get something like gold to dissolve to be in liquid phase. But it also could be a problem if you have some toxic metal, right? And you're like, ooh, didn't want that. There's another potential problem. So for example, humic material, that's kind of soil organics. I put a little tea bag there to show kind of an example that would be more like tannins, but certain molecules you'll find in organic matter, like generic organic matter from leaves or soils or things, they can act as ligands to grab metals and stabilize them. But that could affect the bioavailability. So if you are trying to get more iron in your diet, pro tip is to not go for spinach. You probably heard that a lot. Spinach has a lot of these chelating agents, so it can grab the iron pretty well, but that makes it difficult for your body to grab it away from those chelating agents. So there's that equilibrium to fight there. So something that has chelated it in a more similar manner as our bodies have, like red meat, would actually be a much more bioavailable source, because you've got heme iron, the hemoglobin type stuff, like our bodies use, that would be much easier to take up. So if you're looking at certain things like that, if you're iron deficient, you know, maybe something to consider. So we could potentially use that to manipulate toxics, to grab them, secure them away, or we might be concerned about, oh, you know, what kind of chemistry might draw these out of the soil and become a problem. So example of reducing the toxicity, perhaps we could take a look at aluminum. Al3+ is actually pretty toxic to fish, but it doesn't tend to hang out in that form because it's easy to react with hydroxide in water to form aluminum hydroxides, AlOH3. That tends to precipitate out very quickly. In fact, we often add aluminum sulfate in water treatment as a way to destabilize particles, and then we precipitate the aluminum back out. And it's quite effective. We put it at the right conditions, we'll see that that becomes a solid. And then we have a nice treatment with very little aluminum left. Let's say that's going to become a solid, and we're not risking much at a pretty much a neutral pH. It's almost all going to come back out of solution. Aluminum fluoride is another complex we could look at, ALF2+ or ALF2 1+. Both of those are similar, not very toxic, and can be a way to mitigate aluminum toxicity at low pHs. Okay, so we can see the net charge can be relevant here. We can just kind of think of a few different examples of when the complexation or chelating could be important. So I want to go into just a little bit more about how the different complexations can happen. Now, we could go through a lot more. The book actually has a few sections on whole classifications of different, ligand classifications, what's strong, what's weak, blah, blah, blah. I'm not going to quite go there. I think it's just let you know there's more to classify and to get rules of thumb about, is it going to be a strong one? Is it going to be a weak one? There's some information out there. But to be a little quicker here, let's talk about whether or not water is the front line. So an inner sphere or a true complex is when we've kicked out the water. We said, water, you're not good enough. We're going to attach directly to the metal. So an inner sphere complex is going to tend to be stronger. It's been strong enough with a reaction to kick out the water, and you get a physically closer interaction, meaning you're going to have a stronger connection there. So it's going to replace the hydration, and you've probably seen the water complexation called hydration before. Maybe a hydration layer or a hydrated something. That would be the water molecules complexing. So we're going to replace the hydration, and then we're going to have our electron orbitals directly overlapping. That means that all those really strong but short-range forces, the quantum, the magnetic, things like that, the forces on those levels are linked up and giving a nice strong ligand attachment. Okay, so formally we'll say the electron orbital of the ligand overlaps with the empty bonding orbital of the metal. Yeah?
So does that essentially just describe the mechanism of donating or accepting electrons?
Exactly. So that's the mechanism that it's sharing those electrons, and a little more technical way to say it. So we've talked about the coordination number. I mentioned already it depends on the orbitals, SPD, and so on. Some metals, uranium 4+, can have 12 bonding sites. So occasionally we have some interesting ones. Usually they're even numbers. There are a few that have odd numbers, oddballs. And we could imagine they can have a certain arrangement or shape based on the electron orbitals that we're looking at that are available to bond. So we could have tetrahedral, octahedral. We could have kind of a planar situation. There are a variety of different setups. Then we have, a little more elaboration on that. So we could have something even linear. The gold was an example. I think we said Cl with a gold atom and another Cl, where it's kind of one straight linear line. Another famous example that if you ever work with mercury, you should keep this one in mind. If you get dimethyl mercury, it is extraordinarily toxic and dangerous. If you ever want a horror story from chemistry, look up dimethyl mercury. There was a famous incident where a woman was working with it as a researcher, and she was very aware of the dangers, being very, very careful, but she did get a drop of it on a glove, and she wasn't wearing, I think the thing was she was just wearing a pretty typical laboratory glove, and she needed to be wearing something more because it went through the glove, contacted her skin, through the skin, and it was weeks later, it was a very tiny drop. Weeks later, she began suffering and died of the toxicity because it's just that extremely potent. And it's just, yeah, so don't mess with dimethylmercury. I think nobody ever does that these days. So that's bad stuff. So if you want a horror story, go read up on that. I think that was in the 90s. Okay, so you can have a linear coordination number of 2. Things like gold, mercury, probably platinum, that don't really like to interact too much with other stuff. Maybe those are the ones that be like, okay, well, fine, I'll have 2. 4 is pretty typical. That could be tetrahedral, planar, or square. Kind of mentioned that already. We could have octahedral. That sounds funny because that's a coordination number of 6. Octa usually means 8, but if you look at it, I think that's 8 planes. So you could make a 8-sided die with 6 corners. Okay, is how to think about that. So you can have different coordination numbers, different geometries, stuff like that. Okay, when we have outer sphere complexes, we keep the water layer. So there's going to be, the water is still there, and the water itself is really the thing that's acting primarily like the complexing agent. But we can still have some sort of ligand that adds to that and still gives some stabilization or some favorable interaction for this metal with the rest of the solution. These do generally tend to be weaker, so easier to lose these or swap these. And so we can look at something called the bond strength, K, so some equilibrium constant for bond strength. We could go into this Fuas equation, if I said that right, and how to calculate all that. We're not going to. I'm just saying there's a way to do that. And you can think of this as the water layer itself is likely going to be a couple of angstroms. And an angstrom is a tenth of a nanometer. So it's 10 to the minus 10 meters. So 1 angstrom is 0.1 nanometer. And so the distance here is probably 1 to 2 angstroms.
That's the distance from the metal to the light.
To the edge of the water shell. And so then, to the ligand out there.
So it would be more appropriate to say that it's more or less like an extended radius?
Yeah, so it's basically going to extend the radius between the metal and the ligand. And I don't know, I've heard it both ligand and ligand. I just stuck in my head as ligand. I'm not sure if that's correct. So pick your poison, I guess. Okay. So in general, these are weaker. That's not an exhaustive assumption to make, but generally it would be fine. That would be the best guess. If you had to guess, you would guess that the outer shell complexes have a weaker binding. Okay, so a few other factors that will affect the strength of the binding. Part of it's going to be electronegativity. So if you recall, we have, as we move to the right on a periodic table, which this is something of a periodic table here. It's not exact, but it's showing some metals here. Our electronegativity is increasing as we go to the right. and also increasing as we go upwards. I'm just going to do that. Okay, so if we take a look then, fluoride tends to be our most electronegative species. Now the noble ones are a little funny, right? You'd have to tear away an electron before those were really doing anything. They're just kind of happy. So if we ignore those for a second, fluoride is the most electronegative, right? That's kind of following this trend. So those tend to be give a stronger bond. Size will also make a difference. Will have an impact here where if you are physically closer and not taking up too much room, not bumping into your neighboring ligands, that's easier. That makes for a stronger, better contact. The size of the metal itself might also matter because likewise, if you had a very small metal and then bulky ligands, they might be sharing too much space and kind of pushing each other away, right? So there's a few reasons why at that atomic level we might have some properties of the metal itself that matter, and also properties of the ligand. So if the ligand is inner versus outer, how many bonding sites does it have? And the metal is maybe more so, are we thinking how electropositive is it? The more positive it is, the more it wants to share those electrons. That would generally mean it's going to be a stronger, it's going to form a stronger bond. Okay, make sense?
Wait, you said that the smaller that the complex is, the stronger the bond would be.
It's going to depend a little bit. So I think if you have lots of ligands that are too big, they're not going to complex very well. If you have a large metal ion, it's probably not going to have that kind of trouble. So when we take a look at the metal ion properties, if we're just thinking about the metal, I think the size will have some impact. And I'm not going to give you a hard and fast rule here, okay? I'm just going to say it can matter. If depending on your chelating, your ligands, that kind of stuff, there are factors that can influence it. So I'm not going to quiz you on what directionality there is here on the size, just that it can have an impact.
And in terms of the electronegativity, they're ideally supposed to be like the most positive, or the least electronegative.
Yeah, you can actually say the inverse is electropositive. So you can say highly electropositive metals will end up having a stronger interaction with your electronegative ligands, right? Kind of by definition. Okay, so we can take a look and look at a bit of data. We have a plot here showing the cation, so the metal electronegativity on the x-axis. And on the y-axis, this is the log of the strength of our bond. It's the equilibrium constant, really. But the higher we go, the stronger the bonding. And we can take a look for different, we've got data points for different ligands. So if we use carbonate, monophosphate, or the HPO4 2-, and bicarbonate and sulfate. So we see some of these depend on how electronegative or electropositive the metal is. Some of them don't really so much. So we see different trends just to kind of show you that it depends a bit, right? But we can generally see that trend depending on the ligand that we're using. Okay, for the ligands in particular, we've got the bonding sites, the size of the rings that we form. So we saw some of these that are multidentate. They kind of have a few rings. They're going to end up shaping like a claw around the metal. Those things are two of the properties that matter. And then sometimes it's what atom itself is going to be the electron sharer. Is it a nitrogen? Is it an oxygen? Is it something else? Do we have sulfur? The type of, the nature of the ligand atom is going to have some impact. In general, we could say that the more bonding sites on a ligand that's going to chelate, the stronger it gets, up to about 5. So once you have 5 fingers on the ball, any more fingers start getting in your way. That's the example where, you know, if your hand was rigid and you can't bend it too much, no matter how sticky those sites are, you can't wrap all the way around the ball. And so then you have a problem. It's a bad example, but you get it. Then for stability, nitrogen tends to be let's see what I wrote doesn't really make too much sense. Sorry, I've confused myself here. I grabbed some notes and didn't look closely enough at this last time. I don't know what this means.
So the chelating agents are they basically the same thing as the ligand?
Okay, so yeah, let me explain that. Anything that is sharing the electron with a metal and complexing it is a ligand or ligand. A chelating agent is one of those that is at bidentate or multidentate and grabs it with multiple spots. So chelating.
So it has to be bidentate or multidentate.
Has to have more than one spot.
Under those conditions, the ligand can be a chelating agent.
Yes. So all chelating agents would be considered a ligand. Not all ligands are chelating agents. Okay, so the chelating agent is a subset of ligands, and we use that to describe where it's grabbing with more than one spot. So you can ignore this spot. I'll try to come back and figure out what I was trying to say last time I used this slide. It looks like perhaps nitrogen is a better bonder than oxygen, but I'll clear that up before we say anything for sure. Okay. So we've got a few examples here. Citrate is one of them. So we've got oxalate, succinate, malonate, glycine, ethylene diamine, and some reference. I'm not sure where the citrate is coming from. You've probably heard of some of these, right? Oxalates, and are you ingesting a lot of oxalates? Watch out for kidney stones or something. That's going to be the chelating process, bringing in more metals that your kidney is dealing with, right? So that's going to be this type of dynamic coming to play. So what we're seeing here is several metals on the x-axis, and on the y-axis, the strength of that bond. This is a log scale for that equilibrium constant for that particular ligand. And we can see, for example, some of these interact very strongly with copper. Copper seems to be chelated very well by all of these or the best of these metals. And we can see some are going to work better, be stronger than others. Okay, and maybe this will explain what I was curious about. So I'm going to read this caption because that's probably where I got the other piece. So stability constants across this order of metal atoms, which I think is a specific grouping or order that somebody came up with, follow two trends for bidentate ligands. First, when we have so nitrogen bonded to a nitrogen. Do we have that? That might be. No. Okay, I'm just going to read it. First, nitrogen. Nitrogen greater than nitrogen. Oxygen greater than oxygen. Let's see.
Wait, is it that nitrogen-nitrogen bonds are greater than nitrogen-oxygen bonds, which are greater than oxygen-oxygen?
Yeah, it could be something like that. My brain's not all the way on.
I mean, that should make sense since, it's 3 bonds per.
But we shouldn't have any nitrogen-nitrogen bonds with a metal. Okay, these are bidentate, so there's 2 bonds for each one, right? So if there's 2 nitrogens bonding with the metal, that's stronger than, okay. So this is for bidentate. So yeah, if we have 2 nitrogens bonding to the metal, that's stronger than a nitrogen and oxygen, and that's stronger than 2 oxygens bonding with it. So I'm gonna do this. This is for bidentate. So nitrogen, that's stronger than a metal that's bound with a nitrogen and an oxygen, and that's stronger than a metal that's bound with 2 oxygens. Whatever is between them. So that's what this is saying. When we have this bidentate chelating agent, if we've got 2 nitrogens, that's better than the others. So nitrogen in that sense tends to improve that process, which makes some sense because we said it depended a bit on electronegativity, and oxygen is going to be a little different anyway. In terms of bonding capability. It's actually more electronegative, so maybe that's not directly helpful. Okay, so let's talk about these equilibrium constants. Okay, this is kind of the strength of our binding. Well, what can affect it? There's 2 ways to figure out the equilibrium here. And this is where, if we wanted to know exactly the speciation of a metal in water, just like in the past we were interested in, okay, how much of our acid is an HA versus A minus? Well, we can think for a metal, we might want to know how much is in the highly toxic form, chelated by 2 waters and 2 ammonias compared to some other form. Okay, so sometimes we really need to know this type of information. So how do we get there? Well, we can do it stepwise with an equilibrium constant for each individual complex that we can form, or we can do it cumulatively with this beta formulation. That tends to be simpler. And we accumulate the influence of the entire thing. We're not going to solve any of these big equations all the way out, but we're going to walk through the steps. I said this earlier. We're going to take a look at what it would take to get there. And you'll be able to track with me on it. So each time we remove a water, that's an equilibrium reaction. If we replace it with some other ligand, that's an equilibrium reaction. But the water itself is also an equilibrium reaction, so we need an equilibrium reaction for that too. So anytime we're doing an equilibrium reaction, let's say we have a coordination number of 2. We've got the equilibrium for the first water, equilibrium for the second water, and then we add something else that's interacting. We have a third and a fourth equilibrium reaction for each of those additional reactions. So we get a lot of equilibrium reactions put all together. So let's take a look at hydroxide and ammonia. So hydroxide is when we bond an OH minus with a surface, or maybe we just take water on the surface and then the loss of the proton from it to get OH minus, and ammonia being NH3.
With this, with the equilibrium constant, is this just with respect to the inner complexation shells? This is when water is being taken off.
Yeah. So we're gonna assume both of these are inner sphere. And what we're going to look at really is something like a metal with a plus something charge in equilibrium with, we'll say, M complexed with a water. Still going to have with water, it's just going to still be the plus n charge, n plus charge. And then that will also be in equilibrium with H plus and M with an n minus 1 charge. And complex with OH. I guess I probably could write that better. We'll do this. Okay, so when I'm talking about the equilibrium reactions here, this is kind of what I'm referring to. Each step, we need an equilibrium reaction. Okay, so let's follow along here. So hydrolysis. Hydrolysis is when we're going to change that water, that inner sphere water, for OH. So we're going to lose a proton. This typically happens very quick. And so that first part of the equilibrium that I was just talking about, we can kind of say the overall reaction will be some metal with some hydroxide, or some water, excuse me, OH2. And I apologize, grabbing from the book, our primary book is a little difficult, but this is MEOH2, so with X number of waters with an N plus charge plus hydroxide will give us a substitution where we have X minus 1, so 1 less water, and the charge will be N minus 1. Plus a water. Okay, so basically we're just going to kick off a water and replace for an OH minus. We're going to simplify that and say this is metal reacting with OH minus. Okay, so technically speaking, we're dealing with the water, but we can just say it this way. Then we have a metal OH with an N minus 1 charge. If we want to, we can talk about it in terms of losing a proton. But we'll give this, for example, a K1. And that'll be the first one we look at for the equilibrium reaction. So let's take zinc. Zinc has a coordination number of 4. So I'm going to go ahead and say for zinc, 2 plus, the coordination number equals 4. So we need to bond it with 4 different ligands, or a total of 4 bonding sites. And since we're doing hydroxide and ammonia, that'll be 4 different molecules. So we can do each individual step, saying this first one, like I mentioned, is K1. And we can derive some sort of rate constant. We can find that, maybe do it with thermodynamics. And we can define, of course, that's the products over the reactants. Right? We've seen this. We've done that. Now we're just going to expand on it and keep going and going and going until our brains hurt. Okay? So we're just going to follow along. We can do the next one, where ZnOH plus, so Zn normally has a 2 plus, so when we add the minus, we make it a 1 plus. So now we have ZnOH1 plus an OH minus, we get a zero charge, ZnOH2. That's K2. So we have now 2 of them. We can make a third with a third hydroxide to do ZnOH3 minus. And a fourth one, ZnOH4, 2 minus. So you can see we've gone from a zinc that doesn't really hang out alone, and maybe we could just call it waters, and then we're losing the waters, and then we're adding hydroxides one by one. And if each of these has a minus charge, then our net is now a minus 2. Okay? So, as you might be able to see, if we're using 4 different equilibrium constants, it's going to be a little difficult to solve for what's the total zinc concentration here, if it's in all 4 of these states, right? We have a mass balance. We could say, when we did the alpha fractions, we said, hey, well, the total concentration is in what's in A minus plus what's in HA. So we could say zinc total times alpha 1 plus alpha 2 times zinc total plus alpha 3 times zinc total, all of that, right? So we could look at all those pieces. This would be pretty annoying. So maybe we use these beta, the cumulative versions, could simplify things. Don't worry too much about this. I just want to show you a little bit of how it could work, okay? How we could get there. So if we have these Ks and we say to ourselves, well, let's simplify a bit. Let's use a beta. We could say, all right, well, zinc with water, that's a very first starting point. We could perhaps consolidate that by multiplying the K1, which we got from the zinc plus the OH minus, with the water, KW, multiply them together and call that beta 1. So that's could help simplify. Then we have K2 and beta 1. And we need another water because we didn't really, so we could accumulate these into beta 2, beta 3, and beta 4. So the beta here is going to combine our 2 reactions, the equilibrium of the zinc with the OH minus and the equilibrium of water to get us the OH minus in the first place. So beta here combines K water and Kn. Okay, so that's the purpose of the beta. And then what we can do is say the zinc total now is some function of how much zinc 2 plus we have in solution times this function here. And it's going to be the zinc 2 plus times 1 plus each fraction. So this is the fraction that is zinc 2 plus. The next one is the fraction that is zinc with 1 hydroxide, then the next with 2 hydroxides, and so on. So we can just build this out into an elaborate scheme here where we have no hydroxides, then 1 hydroxide, 2 hydroxides, 3 hydroxides, and 4 hydroxides. Okay. Yeah.
To find beta sub n, can multiply KW by K1 or KI?
I think that's what they're basically showing here, right? So if we to get our, or no, we need to combine the previous beta 2, I think. So to get beta 2, we combined K2, beta 1, and KW. And that's why it's cumulative in that regard. Okay, when we add ammonia, things get even a little more complicated. So now, if we add ammonia into the water, not only do we have the water and the potential for the OH for the water to lose a proton, now we have ammonia wanting to chelate it as well. So we could go through the same process, say, okay, here's K1 through 4, and we have an equilibrium for each of those, and we can get the beta values by combining the ammonia equilibrium and these Ligand equilibriums, so that we could say, all right, here's beta 1, 2, 3, and 4, multiplying the K's together that way. So at the end of all of that, we could generalize this to a kind of any system, any similar system, and what we'll find is that we get a very nice but complicated formula here, where we can get the total zinc in a water system that also has ammonia, could be found by this. Now, each one of these is describing a different species. So the first one is however much is in just simply the zinc 2+. Now, we said from the beginning that that doesn't happen much, but I think this is actually referring to the hydrated. So all waters, no OH minuses attached. So then the next one is waters except 1 OH minus, 2 OH minus, 3, and so on. And then beta 2 would be, then beta 1 times NH3, that would be, I think that should be all waters with 1 ammonia. Yeah, I think that's correct. All waters with 2 ammonia, 3 ammonia, or just 4 ammonia. Okay, so that gives us 8 different species of zinc in there. Well, really 9, I guess, if you're including the ZN2+. So depending on how you think about it, 8 or 9 different species, all within that one equation. And kind of makes your brain hurt a little bit. So let's take a system containing 10 to the minus 7 moles per liter of zinc 2+ total, and 10 to the minus 3 moles per liter of total ammonia at pH 9.25. What are the concentrations of free zinc and the 8 complexes in that equation? All right, go. I'm just kidding. Okay, so let's think about it for a moment, because we could just look back at that equation and recognize, okay, this is the free zinc, and then I can find the next one by finding this times this, right? And we can go down the list and say, okay, here's the concentration for a given species, right? That's kind of the objective. So let's just take a quick look at what this problem is functionally doing, so we can kind of get a feel for what this is like. And by the way, this might be something that I've been working with you on Excel and MATLAB, but there's also some pre-programmed equilibrium chemistry software out there. Visual Mintech is a good example, and I think our books talk about that. So you can find stuff that do these types of computations, and it's there. It's built in. You set the temperature, you tell it what you need, and you can get the speciation pretty quick. So this is to kind of understand what would be behind that, how that calculation would work. So we begin with the ammonia equilibrium. We have NH3 in equilibrium with NH4+. It turns out we were given the pH of 9.25, which means we're right at the pKa. It's very handy. So automatically we know we have 50-50 in terms of NH3 and NH4+. Okay, we can treat this, the ammonia separately, because even if all 10 to the minus 7 moles per liter of zinc were complexed by 4 ammonia molecules, there would only be a very tiny amount of ammonia taken away. So we have so much ammonia that it doesn't matter if we take some of it away. We can treat it as if we just have plenty of it. That's what it's saying. Okay, so we're not worried about that. Good. The pKa is right at the pKa for ammonia, so then that means we have, for the NH3, which is the thing we're interested in, for the complexation, it's exactly half of the total. Okay, 5 times 10 to the minus 4th. Great. Okay, so now we can start adding in, substituting in some numbers here. And because we just derived all this, we have some values that we can work with. So into that equation, we know we have some H+. Let me flip back to the equation and we'll take a look at what we know. So I think we were talking about this in the previous slide, so I think we know those. We have H+, we're given that. We know something about the total amount of zinc, and we're going to know how much ammonia we have. Okay, so we actually know almost all of this, so we're just going to then piece it together. Oh, sorry, I pressed the wrong button. Press end. Okay, so for this equation, they write in those numbers. So yeah, we did get the beta values from the previous slides. And then really it's just about the numbers, like putting in all the numbers. So from the above equations, we see that the first 2 hydroxy complexes have higher concentration than zinc 2+. So these 2 numbers are going to be greater than 1. It's 10 to the minus 8.9 divided by 10 to the minus 9.2. That gives us a fraction that is greater than 1. So it's more concentrated than just the zinc by itself, is what it's saying. All the others, I think, are smaller. So the numerator is smaller than the denominator. Okay, and the ammonia complexes have lower concentration than all but one of the hydroxy complexes. Substituting the value for zinc total and dividing the terms in the parentheses gives us our zinc 2 concentration of 2.3 times 10 to the minus 9. So we could put all that together, do that math to find our free zinc concentration there. And then from there we could determine each of the complex concentrations by multiplying this value to the appropriate term. So, headache, yes. Possible, also yes. Yeah.
So you essentially just take every reaction mechanism stepwise to find each respective beta, and then you can plug that in there.
Yeah. Okay. Makes some sense. At least followed it kind of mostly the process, big picture process. Okay. So the point of this is it's all equilibrium chemistry, and it's a lot of equilibrium chemistry. That's kind of the deal. And now you can get a feel for when something's complexing, when we talk about chelating, solubility, or bioavailability or something like that, we can see, oh, okay, it's not that you will get 0 iron from eating a bunch of spinach. It just, you might not be taking as much as you thought. If the package on the spinach says it gives you 5 grams of iron, well, maybe only a portion of that is going to fractionate into a bioavailable form, right? That's kind of the takeaway from all that. Oh, and here is each of these reactions written out for you, or the species. Okay, one practical example I'd like to leave you with here is black and white photos. So I found online a nice black and white photo of Mike the tiger, or some other tiger, I don't know. So Silver bromide, AgBr, is a soluble that is pretty much insoluble. If you wash it, it's not going to go anywhere. So if you make a film with a bunch of silver bromide, you pour water over it, nothing happens. It's just going to stay there. So you make a film out of this because silver bromide is light sensitive and will convert the silver to a zero-valent zero-valent silver instead of the 1+, because bromide is 1-. So it'll go from 1+ to zero-valent. Zero-valent is metallic silver, so it will then be solid, and it will be happy to sit there, also insoluble. So if you expose it to light carefully, then whatever photons were absorbed now are stuck in terms of a metallic silver. Then you process your film to remove the remaining silver bromide, but that's a solid, so wait, how do you do that? Well, you add some sort of chelating agent. It's not going to stick to the metallic, the zero-valent, but if so we have this solubility product here, Ag+ and Br- for the solubility. It's not very soluble, but we add thiosulfate. And here's that Le Chatelier's principle that says, if you can drive a reaction in equilibrium one way or the other. So it turns out silver plus is complexed nicely by thiosulfate, and it looks like this. And you can see this is silver here has a coordination number of 2, and we are bonding with each thiosulfate with a sulfur group, and apparently that has a pretty good binding constant. So if you then wash it with a solution of thiosulfate, what you will do is you'll remove all the remaining stuff that would be sensitive to light. So you make a film, it's got a nice consistent layer of silver bromide, flash some light on it, then you take it into the dark to stop shining any light on it, then you wash it with a solution that has this thiosulfate. Once it's clean, you're left with just some silver on that film. There's your black and white photograph. Okay? Here would be the just a quick look at the equilibrium constants and the equilibrium equations. We've got silver bromide, not very soluble, 10 to the minus 13. Then we add the thiosulfate. Suddenly, that's pretty high binding energy, or binding strength, so it is solubilizing it, and we can get rid of it. We can combine those two K values. That's kind of like what we did with the beta to get K of 15 there. Okay. Any questions? All right. So we'll pick up there next time.